What happens? When you actually test cheap versus expensive filament, you've seen the debate 100 times. Someone posts a spool of $12 filament in a 3D printing forum, and within minutes the comments are divided. Half the people say it's perfectly fine. The other half act like you just announced you're printing with wet cardboard. So who's right? The honest answer is that most people arguing about filament price have never actually tested it. Not really, not in a way that tells you anything useful. They printed a benchy, it looked okay, and they called it a day. Or it strung badly and they threw the whole spool in the trash. Neither of those tells you what you actually need to know. So let's change that. Let's run real tests, look at what the results actually mean, and figure out whether spending more on filament is genuinely worth it, or whether you've been paying for a brand name this whole time. First, let's talk about what you're actually buying when you buy a spool of PLA, because most people think filament is just plastic. Melt it, push it through a nozzle, it sticks together. Done. But the reality is a lot more interesting than that. PLA, polylactic acid, is a polymer. A polymer is just a long chain of repeating molecular units. The length of those chains, how consistent they are, and what gets mixed into the material all have a massive effect on how it behaves in your printer and in the finished part. Premium manufacturers tightly control the molecular weight of the polymer, the moisture content of the pellets before extrusion, and the diameter consistency of the finished filament. Cheaper manufacturers may not. That last one, diameter consistency, is the one that affects you most visibly. Every FDM printer assumes your filament is exactly the diameter it says on the spool. Your slicer calculates how far to push the filament based on that number. If your filament is actually 1.72 millimeters in one spot and 1.78 millimeters 6 inches later, your printer doesn't know. It just keeps pushing at the same rate. And what you get is inconsistent extrusion, thin walls, gaps in infill, rough surfaces, and weak layer adhesion in spots you can't predict. So for the first test, grab a pair of digital calipers and measure a cheap spool and an expensive spool in 10 spots along the filament, spaced roughly a meter apart. Write down every number. The cheap spool might average right at 1.75 millimeters, but the variance might be plus or minus 0.08 millimeters. A premium spool might hold within plus or minus 0.02 millimeters across every measurement. That seems small. It isn't. Over the course of a long print, that variance accumulates. The difference between a part that passes a snap fit tolerance check and one that doesn't is often less than 0.1 millimeters. Now let's talk about what actually matters for most makers: mechanical strength. Here's something that surprises a lot of beginners. The strength of a 3D printed part is not mostly about the material, it's mostly about print settings and orientation. A well-tuned print in cheap filament will outperform a poorly tuned print in premium filament almost every time. So when you test filament strength, you have to hold every setting constant. Same printer, same temperature, same layer height, same infill, same orientation, and only change the filament. Otherwise, you're not testing the filament, you're testing your settings. For a tensile strength test, that's how much force it takes to pull a part apart, print a simple dog bone-shaped test specimen in both filaments at identical settings. Clamp both ends in a vise or a tensile tester and pull until failure. Look at two things: how much force it took and how it failed. A brittle failure looks like a clean snap with a glassy fracture surface. A ductile failure shows whitening, stretching, and a rough fracture surface. PLA tends toward brittle failure in general, but higher quality PLA often shows more ductile behavior before final fracture, meaning it absorbs more energy before it lets go. In functional parts, especially anything that takes impact, loading like brackets, enclosures, or tool holders, that energy absorption is the difference between a part that survives and one that explodes. What about layer adhesion specifically? This is where cheap filament can really let you down. Layer adhesion, how well each layer bonds to the one below it, depends on how well the material flows, how clean it is, and how consistent its thermal properties are. When cheap filament has inconsistent moisture content, because it wasn't dried properly at the factory or sat in a humid warehouse, Water in the material turns to steam inside your hot end and creates micro bubbles in your extrusion. You might hear a faint popping sound. Your extrusion looks slightly foamy, and your layer lines don't bond cleanly. You can test this directly. Print a wall, just a single wall, 2 layers wide, about 80 millimeters tall. Then try to peel the layers apart with your fingernails or a knife. Compare how much force it takes on a cheap spool versus a premium one. On a poorly bonded print, the layers will delaminate with almost no effort. On a well-bonded print, you'll damage the material before the layers separate. This matters enormously for any print under mechanical load, especially parts loaded in tension perpendicular to the layer lines. That's the weakest direction in any FDM print, and cheap filament with moisture contamination can make it dramatically weaker. Now let's talk about something that almost nobody discusses: dimensional accuracy. Not just diameter consistency in the raw filament, but how accurately your finished print matches the design. Different PLA formulations shrink differently as they cool. Shrinkage rates vary between manufacturers and even between color variants from the same manufacturer because pigments affect the thermal properties of the material. A black PLA and a white PLA from the same brand might have slightly different shrinkage, which means your 20mm calibration cube might come out 19.87 millimeters in one and 20.02 millimeters in the other. If you're printing anything with mating parts, snap fits, or press fits, you need to know your filament's actual shrinkage and account for it in your slicer compensation settings. Premium filaments usually publish their shrinkage data. Cheap filaments often don't, which means you're tuning by trial and error. This is especially relevant for functional hardware. If you're printing enclosure clips, camera mounts, jig fixtures, or any part that interfaces with off-the-shelf hardware like M3 bolts or standard bearings, your tolerances need to be consistent. With a known consistent filament, you can dial in your tolerance offsets once and trust them across future prints. With a cheap spool that varies batch to batch, you're recalibrating constantly. So what's the practical takeaway here? Cheap filament is not always bad. If you're printing prototypes, test parts, visual models, cosplay props, or anything where mechanical performance and precision don't matter much, a quality budget filament from a reputable manufacturer, someone who publishes their tolerance specs, is often perfectly fine. The benchy will look great. The bracket for your desk lamp will hold. But if you're printing functional mechanical parts, snap fit assemblies, parts under load, or anything where dimensional accuracy matters, the extra few dollars per kilogram for a premium filament is not buying you a brand name. It's buying you tighter diameter tolerance, better moisture control, more consistent shrinkage data, and better layer adhesion. Those things translate directly to more reliable prints, fewer failures, less wasted time, and parts that actually perform the way you design them. There's one more thing worth testing that most people overlook entirely: printability. How easy is the filament to work with? Does it clog? Does it string? Does it warp on the first layer? Does it need a very specific temperature to flow well? Premium filaments tend to have a wider processing window, the range of temperatures and speeds where they print reliably. That means if your printer runs a little hot or your environment is drafty, you still get a good result. Cheap filaments sometimes have a very narrow window where they behave well, and outside that window they become a nightmare. So before you commit to a new filament, cheap or expensive, print a temperature tower. This is a single print that increments temperature in steps, usually in 5-degree intervals across a range from maybe 195 degrees Celsius to 225 degrees Celsius for PLA. Look at each segment and judge: surface quality, stringing, layer adhesion, overhang performance. Find the best temperature for that specific filament and use it. Treat every new spool like it has its own personality, because it kind of does. At the end of the day, the best filament is the one you understand. Know your diameter variance, know your optimal temperature, know your shrinkage. Dry it before you use it. Almost every filament benefits from a few hours in a dryer or oven at 45 degrees Celsius. And test your parts before you depend on them. The $12 spool might be exactly what you need for most of what you print. The $30 spool might be essential for the parts that actually matter. Now you know how to tell the difference, and you can make that call based on data instead of forum arguments. Go print a dog bone, pull it apart, and see what your filament is actually made of.